All right, so this is section 6.3 about logarithmic functions. Before we get started, just a word about one of the applications of logarithmic functions is the Richter scale. And so the Richter scale is used to measure the intensity of earthquakes. Oftentimes, though, I feel as people don't really understand how those readings work. And so the intensity of a Richter scale for earthquake actually has an intensity of 10 to the fourth power. And the magnitude 8 has an intensity of 10 to the 8th power. So this is not kind of this relationship where, 4 times 2 is 8. It's twice as strong. Instead, what we're actually seeing is this relationship right here. So the difference is actually 10,000 times more intense from a magnitude 4 to a magnitude 8. And so that indicates that we're dealing with an exponential and logarithmic relationship because things are getting big very, very fast. So the definition of a logarithmic function, it's very closely related to the exponential function. A logarithm of base b of some positive number x satisfies this definition. So we can see here the parallel between the logarithm and the exponential. These two are equivalent, and we're just kind of changing around the location of the variables in order to do that. So that's going to be one of the tools that we use to analyze logarithms. We read that as the log base b of x is the most common way you'll hear it. And the logarithm is actually the exponent that we have to raise the base b to get x. And so think about it like this. So the log base b of x equals y is equivalent to thinking b to the y equals x. And so similarly, the log base b of some number c equaling a means that b to the a power equals c. And so this just kind of, when you read it, if you want to move it to the exponential form, b to the a equals c. And so you can kind of use that visual to help you out a little bit. And another important thing is that if we compare the logarithmic function to the exponential function, we find that the input and outputs are switched. And this is because of that exact same relationship we saw before between the logarithm and the exponential. These are inverse functions. And so another note about the logarithm, this is an important question. Can we take the logarithm of a negative number? And the answer is actually no. Because we define the base b to always be positive, there's no power of a negative base that can ever be negative. And so we can never take the logarithm of a negative number. It's considered to be undefined in the real numbers, so we don't do that. If you have complex numbers, maybe, but in general right now we're working in the real number system. So this is a no. And you also cannot take the logarithm of 0, and that's because there is no power of b that will ever equal 0. That's never going to happen, so we do not have any success trying to take the logarithm of 0 or the natural logarithm of 0. So just some side notes. So again, as mentioned previously, one of our big tools here is going to be converting from the logarithmic form here, log base b of x equals y, to the exponential form. And recall that exponential form is b to the y equals x. And so in example 1, we're going to convert from the logarithmic form of this equation to the exponential form. And so one of the things I like to do while I'm really looking at this is I like to write this general format until I kind of get the hang of it. So we'll take this log base b of x equals y and transform it into b to the y power equals x. And that's just by taking all of these things. So we're really going to pick it apart, this first one. So for a, The base b is 6. X, or what we call the argument of the logarithm, is the square root of 6. And y is equal to 1/2. And so when we rewrite this, we're just going to rewrite it in this format. And we'll find that this is 6 to the 1/2 power equals the square root of 6, which we know by properties of rational exponents that that is in fact true. So again, now let's try it with number or letter b. So this would be the base b to the y equals x. And that is in fact a true statement. So we've transformed that from the logarithmic to the exponential form in this case. And then if you'd like to try, I encourage you to do that. Pause the video and see how you do. All right, so for A, we're going to have 10 to the 6th power equals 1,000,000. And for B, we're going to have 5 squared equals 25. We know that those relationships hold, and you can easily check that in a calculator. So again, let's go the other direction. This is an inverse set of functions, so we can do that. So this is converting exponential to logarithmic form. And so this time, instead of moving from log base b of x equals y, we're going to move from b to the power y equals x to the log base b of x equals y. So we're just now going in reverse. And so let's look at example A. The base b is 2, the exponent y is 3, and the result is 8. And so now let's convert that over to the logarithmic form. And so that's going to be the log base 2 of 8 equals 3, which we can confirm is correct. So this will be, now let's look at B. So this would be the log base 5 of 25 equals 2. And finally, this one's a little tricky because you have negative exponents in a fraction, but it works exactly the same way. So this is going to be the log base 10 of 1 over 10,000 is equal to -4. Now, the argument, which is this, cannot be negative, but the output or the result of the log function can be a negative number, and that's okay. All right. So for the try it number 2, if you want to give this one a try, and then come back and check your answers and see how you do. This one for A would be the log base 3 of 9 equals 2. For B, we would have the log base 5 of 125 equals 3. And then finally, we would have the log base 2 of 1/2 equals -1. All right, so evaluating a logarithm, we use a similar kind of idea of asking ourselves the question, you know, b to what power equals x? And that's how we kind of do this mentally. So recall the following algebraic rules. Remember that if you have a negative exponent, it can move from the denominator to the numerator or the numerator to the denominator and become a positive exponent. And then also remember for rational or fractional exponents, if we have the nth root, that becomes x to the 1 over n power. And let me just make that a little more clear because the formatting is kind of gross. So that's the 1 over n power for the nth root of x. And we saw that when we were solving for the rate in the compound interest formula. So let's solve this mentally. So we want to ask ourselves for, like this is kind of the question you asked, to 4 to what power equals 64. And if you're not familiar with higher powers of the numbers, so you can just try some, right? And you'll find that 4 to the 3rd power is in fact 64. So we say that log base 4 of 64 is 3, because remember the output of the log function is the exponent in the exponential function. So if you can just ask yourself this question, the power that you come up with is actually the output of the logarithm. So trying that in number 3, give this one a try. It's kind of tricky. All right, so for this, again, we'll ask ourselves 121 to what power is 11? So the first thing I'm going to do, just kind of like knowing my perfect squares, is I know that the square root of 121 is 11. And so I can kind of reimagine that. Instead of the root 2, I can imagine this as a fractional power, which is what I have to have when I'm working with this, since my output or my answer is going to be that fraction. Since 121 to the 1/2 power is 11, the log base 121 of 11 is 1/2. All right, so example 4, evaluating the logarithm of a reciprocal. So a reciprocal is just 1 over a number. And so we're going to kind of have to think this through a little bit. And so I'm just going to start, instead of 1 over 27, I'm going to start with a simpler idea. 3 to what power equals just plain old 27, right? And we'll start there. That won't be our final answer to the question, but we can say that 3 to the 3rd power is equal to 27. And so we can think about this like this. Let's say, how can I get this down into the denominator? Well, so using the properties of negative exponents, so 3 to the negative 3 equals 1 over 3 to the 3, which we already said that 3 over 3 is 27. So this would be 1 over 27. So the power that I'm looking for is, if I raise 3 to the negative 3rd power, I do end up with 1 over 27. So this is when you're going to see these fractions, is when you're going to see these negative outputs for the logarithm when you have something dropping down into the denominator. So that's our answer for this one. So if you want to try one of those in number 4, give it a shot. All right, this one's done similarly, and you'll find that the log base 2 of 1 over 32 is in fact negative 5. And again, you can confirm that in the calculator by transmitting it into the logarithmic form, the exponential form, and that would be 2 to the negative 5th power should equal 1 over 32. Right, so using common logarithms is something that's often done. The common logarithm is just the logarithm base 10. So log base 10 of x, and you'll see it written as just the plain log of x without the base. So if we don't see a base indicated, then that's going to mean it's base 10 or the common logarithm. It's again, what power do I raise 10 to get x? And so 10 to what power equals x is going to be the question I ask when I'm evaluating the common logarithm. So for this, I want to know 10 to what power equals 1,000. And so my answer there, and if you're not familiar with those powers, you can just kind of play around with it until you find something that works. So the log of 1,000 is going to be 3. If you want to give this next one a try. All right, so this would be 6. Now, if you notice, with the log base 10, there were 3 zeros here, and that's a power of 3. And there are 6 zeros here, and that's a power of 6. That's a lovely shortcut when you're looking for powers of 10. The next thing is, you're going to love it. So finding the value of a common logarithm using a calculator. So there are 2 buttons concerning logarithms on your calculator. One of them is the log button, and it does refer to the common or base 10 logarithm, right? So that's all you've got to use other than the natural log on your calculator. So you will literally type this into your calculator and evaluate to 4 decimal places, and you should get that it's approximately 2.5065. And if you want to try it on this one, you can confirm that this is 2.0899. So a real world exponential model, we can also solve these. So this is talking again about the magnitude and the energy released from an earthquake. And it says that the model for this situation is 10 to the x equals 500. Well, unfortunately, 500 is not a nice even power of 10, so we would not be able to guess at this. But what we can do is convert this into logarithmic form. So that's the log base 10 of 500 equals x. And this is something that we can place in our calculator because we do have a common logarithm button. And so let's do that, and we will actually find from the calculator, that x is approximately 2.699. So if you want to try this one, now it's going to be done in a similar way. And you'll find that this is about 3.929 if you want to try it and see if you get the same thing. All right, now let's talk about natural logarithms, which is not a crazy idea. It's just a logarithm with base e. So the idea is this, log base e of x, but you don't see it written that way. We have a shorthand because e is such a common base, as we saw previously with the continuous exponential growth and decay function, that it's so common, in fact, that we give it its own special notation, which is ln, which means natural logarithm. And again, that is just the log base e, and this is just the shorthand notation. And we call it the natural logarithm of x. And it is the exponent to which e must be raised to get a number x. And so we can evaluate these in our calculator as well. There's your how-to box. You'll just need to locate the ln button on your calculator and plunge this in, just this part, not the y, of course. And you'll obtain that this value is approximately 6.2146. And then if you want to try this number 8 example, I encourage you to do that. So you'll see that you got a domain error, right? And that is because it is not possible. If you remember earlier in our definition of the exponential and logarithmic function, it is not possible to evaluate the log of a negative number in the real numbers anyway, right? We could extend this to the complex numbers, but we're not doing that. The negative number in the real numbers. Sad face. I'm so sad. Any case, I'm sure you're not. But that concludes all of what I want you to know from this particular section. So I will